Okay guys, let's start the lecture. Okay, just want to review one of the things that I left myself a question mark, if you remember in the first lecture, right? Yeah. So I did an example, basically what will be the inverse Laplace Ztransform for this particular one, if you remember. Okay. And the technique basically I'm using is I'm trying to match what's given in the Z table. And in the Z table, okay, if you would see that there are two sequence, which is this one, the corresponding Z transform is this and that. Okay, yeah. So apparently this is the one where the denominator match what's given here. And as a matter of fact, the pose of this system, of this fraction right here, is a pair of a complex conjugate number. Okay, so what we do is we're trying to manipulate this to match this one or this one, so that we can basically directly use the table to find the inverse, right? Yeah. Now, during the process, you know, basically what we do is, okay, we look at the denominator and compare the denominator. We said, okay, look at that, a squared, it must be 0.64, right? Yeah. So, and I said, okay, a must be 0.8. So I had a question to myself, can a be negative 0.8? Remember that, right? Yeah. Okay, so the answer is yes. Okay, yeah. But before we see why the answer is yes, what we can do is, you know, if you look at your table, there is another Z transform, and that Z transform is corresponding between this guy and this. Okay, so see the difference here. This is a to the power k, right? And this one here is e to the power negative a k capital T. Okay, yeah. So basically, for this particular term, this particular term comes from a time function. Comes from a time function like this. Okay? Yeah. So you see the difference between this guy and this guy. Okay, the difference between these two is, for this one, we don't really know. If we write this one here, we don't really know what time function this is from. Okay? So all we know is this can generate a sequence of number. That's fine. You know, you plug in different k, it'll give you a sequence of numbers, right? Yeah. But you look at this one here, we will have no idea where that sequence of number is from what kind of time function. Okay. You know what I'm saying, right? So when you see a sequence number, for the first number it's 1, second one is 2, something like that, right? But what is the time duration between these two? We don't really know. Okay, but for this one here, we know that it got to be from here with a certain kind of sampling time t. Okay, yeah, that's the difference. And second of all, the Z transform, this one is this, right? Is this. So if you look at this between this and that, what is the difference between this and that? If I rewrite this e to the power of a k t, which is what? Is that right? So what's in the bracket, right? What's in the bracket is can be basically this small letter a here. Well, already there's a here, but you know, that's basically the analogy at here, right? That makes sense? So the value of e to the power of negative at is always what? Positive, right? So if you use this pair of a transformation here, then you won't have this ambiguity to ask yourself, okay, should I take a positive or negative here? You see what I'm saying, right? Yeah. Basically, if you use this pair of a transformation, you will see, okay, so this one, well, in this particular case, equal 0.64. Okay? Yeah. Is that good? Yeah. Okay. Now, come back to this question here is, if you know, I think in the previous lecture I give you the results. What's the result if I take the A is 0.8, right? Now the question is, if A is negative 0.8, what will be the result? Okay, so to save myself, I think I will leave that as exercise, but I'll give you the results here. Okay, so you can verify yourself. If I take this A is negative 0.8, the inverse Z transform of this one, okay, the inverse Z transform of this one, what I'm going to get is, I'm going to get negative 0.8 to the power of k cosine 2 pi over 3 times k minus 1.4 over 0.4 over root 3 k sine 2 pi over 3k. Okay, so this is the result if I take A equal to negative 0.8. Alright, yeah. And you can look at your previous lecture notes or my lecture notes. You will see that if I take, just maybe rewrite it here, if I take 0.8, I will get a result is 0.8 to the power of k cosine pi over 3k plus okay, I'll get this. Okay, so if you look at these two, okay, they actually seemingly to be different expression here, right? It's actually quite different because this is a 0.8, this is negative 0.8. This is cosine pi over 3k, that's cosine 2 pi over 3k. Okay? Yeah. But, okay, there are two different ways to prove, okay, these two actually will yield the same sequence of numbers. Okay, when you plug in k value, so k equal to 0, 1, 2, okay, these two will yield the same sequence of numbers. Okay. So in other words, if you take Z transform of these two, same sequence number, they should yield the same Z transform, right? Yeah. So try MATLAB Z trans, okay? Okay, use the example to give you in the lecture notes. Try on both of these, you'll get the same Z transform. Okay? And the other way to prove that these two are the same, is to make use of the linear, to make use of the trig identity. So what you do is, you can try yourself. Okay, so I actually try myself. But I just don't want to spend the whole class to go over it. So this 2k over 3, 2k over 3 equal to what? Right? It's pi minus 1/3 of pi. Okay, so this whole chunk here basically is cosine k pi minus pi over 3k. So kind of single out this pi over 3k now. Okay, yeah. Then this cosine k pi minus this, so this cosine k pi minus pi over 3k will equal to cosine k pi cosine pi over 3k minus sine k pi sine pi over 3k, linear algebra trig identity. Okay, that makes sense? Same thing for the sine, you can do that to find it. And sine k pi is always 0. Cosine k pi, when k equals to 0, cosine 0 is 1. When k equal to 1, cosine pi is negative 1. So basically between 1, negative 1, 1, negative 1, they oscillate. So this term is negative 1 to the power of k. Okay? So now you see, if I just look at the first term. If I plug the first term, this back in here, I have a negative 1 to the power of k shows up right here, right? And this is negative 0.8 to the power of k, which is what? Negative 1 to the power of k, negative 0.8 to the power of k. So negative 1 to the power of k times another negative 1 to the power of k is actually 1, right? So basically you will be able to prove that these two are actually the same thing, right? Yeah. So technically speaking, basically the A, right? Because this, you could take the negative value. But to simplify the situation, of course, you know, if you make an analogy to this pair of transformation, you can always just take the A value as 0.8, okay, the positive one. Does that make sense? Yeah. Okay, so second of all, Brad asked a question. If you remember, the question is, can we use the partial fraction expansion on a complex poles, right? Yeah. So basically, the question is, here's a z squared plus z over z squared minus 0.8z plus 0.64, right? Yeah. So we basically, what we do is we write the bottom denominator into two parts, right? The first part basically is the z minus the first pole, and the second part is z minus second pole, right? Okay. So in this particular case, you have two complex conjugate poles. You can verify that, and that turned out to be 0.4 plus minus j 0.4 root 3. Okay, that's the two poles. So basically, I can write this poles, okay, into this bottom here. Okay, that makes sense? Yeah. So then, if I want to do a partial fraction expansion, and this is x of z, if you remember what we do is, we divide both sides by a z, right? Divide both sides by z. So basically, divided by z here, and z here, and then you can imagine the top one here becomes just a z plus 1, right? Okay? Yeah. So ultimately, what you see here is you get two distinct roots, right? But of course, they're complex. So if I want to apply that partial fraction expansion, so I get a over what? Z minus the first pole, it's called P1, and B minus the P1 conjugate, right? Okay, yeah. So how do I find the A and the B? A and B actually we call the residual. Okay. So this is called residual here. Okay. If you want to manually calculate, as we learned, basically the A will equal to Z minus P1 times X over Z, then Z equal to P1, like that, right? Yeah. So you plug it in here, you will get certain A value. Okay. So the A value you will get is 1/2 minus J 1.4 over 0.8, okay, root 3. Okay. And if you use MATLAB, there's a MATLAB is a command just called the residual. Okay. You can use it to calculate. But MATLAB doesn't give you the root 3 right here. It gives you just a real number there, right? You know, sometimes it's good to keep this here actually, particularly when calculating the angles later. Is that good? Yeah. Okay, so similarly can find the B value, right? Okay. So then, what will be the inverse Z-transform? So the inverse Z-transform, according to this table, you would get what? A times. What did you get? What's the inverse of this? A times what? Oh, well, inverse. Basically, when you calculate the inverse, before you calculate the inverse, you're going to have to multiply the z back over here, right? Multiply the z back over here. Okay? Yeah. So, you basically get what's the inverse of this? Which is A times what? P1 to the power of k, right? P1 to the power of k. So, I think what I mentioned in the first lecture was not quite right. I said this is, you can't plot it on the real plane, right? no, truly you can plot this, but what happens is you can make some, you can put them together, you'll be able to make some simplifications, right? So the other portion is you get B, okay, you get this, right? Look at this, okay? Is that good? Yeah. Okay, so now basically here comes, imagine this A is a complex number, right? And P1 conjugate, and apparently they're complex, isn't it, right? They're complex. So what you can do is you can do this steps to here. For this P1, which is 0.4 plus J 0.4 root 3, for any complex number, remember you can always write it into what format? The magnitude times e to the power of j theta, right? For any complex number. So what's the A? A is the magnitude. Okay? So in this particular case, it's 0.8. And what's the theta? So basically, you look at a complex plane. The theta is the inverse tan y over x, right? So in this particular case, it's pi over 3. Yeah. Is that good? Yeah. So then you plug this one into here. So why I'm converting this to this? Because the case power of this is hard to calculate, right? But the case power of this complex. So what does that give you now? So for this one, it's equal to A times 0.8 to the power of k times e to the power of j what? Okay? Yeah? Okay. And the second one here, similarly, you get 0.8 to the power of k e to the power of j negative pi over 3k. Okay? And then you also have the a and the b, which is a is this, and you'll be able to get a b, which is just I think it's just 1/2 plus that thing there. Yeah. So. Okay, yeah. So now the rest of the job is basically the inverse is this plus this, right? Now do it in your head. I'll skip myself. So what happens is what I'm going to do is I'll rewrite this e to the power of j pi over 3. Rewrite this back into the complex a plus jb format. And so this is basically, sorry, did I miss? Oh, sorry, here. So for this term. So for this term, this is what? Cosine plus j. Alright? Okay? Same for this one here. Then you plug this a over here. Plug a over here, plug the b over here. Okay? Yeah. Okay, so this sounds like pretty complicated, but trust me, and because there's complex conjugate things, when you expand everything out, and there's lots of positive and negative things will cancel out each other. Alright? So once you clean out all the picture, the whole thing, you will get exactly the same thing like this. Is that good? Yeah. Okay. So apparently this way here is a bit of a more complicated because it involves a bit more calculations here. The way I did here is essentially I'm trying to match what's given in the table, right? Yeah. Save a little bit of computations. Alright? So that's the case finding inverse when you have complex conjugate poles. Okay, so we continue from a previous lecture, and we talked about impulse sampling, and we talked about zero order hold. Okay. So when we talk about the zero order hold, and basically what will be the, here is a delta t, we call that impulse sampler. Okay. Then if I have a zero order hold, and I'm using, let's say, I'm using a transfer function to represent the mathematical model to represent this system, the zero order hold here. Okay. So there will be something out of here, right? Okay. Okay, so if this is x of t, this is x star of t, something like that, and then you get y of t, for example. Okay? Yeah. So in the previous lecture, we derived the Laplace transformation, or basically the transfer function expression for this zero order hold, and that is, okay, so that is this guy here. Okay, so let's continue from here. Okay, let's continue here. We're going to look at it basically open loop pulse transfer function, okay, particularly. Okay. But before we do that, so let's look at the simple case. Okay, so look at the simple case. Okay. Basically, the idea is, what is a pulse transfer function? Okay, pulse transfer function. Okay, so the keywords, there's a pulse, right? You know, not just a transfer function anymore. Okay. That is mostly basically because, okay, when you're dealing with a digital system, you gotta have this impulse sampler somewhere, okay, in the loop. Okay. Yeah. Okay, so I'm gonna draw another diagram, just like very similar to that one there. So here is a very simple system. A very simple system. You have an impulse sampler, okay, delta t here. Then you have a transfer function h of s. So this could be just a zero order hold. It could be a combination of a zero order hold with some other blocks. Is that good? Yeah. And this is x star of t. This is capital X star of s. And this is y of t. Okay. So we're trying to find the pulse transfer function. Then right now it's actually kind of a mixed things together here. Now if you also remember is from previous lecture, if you remember, how did I get that capital X of z? Capital X of z is obtained, or it's a signification basically of x star of s, right? So once you get x star of s, you can get x of z by replacing the s with what? 1 over t ln z. Okay? Yeah, you'll get x of z. Okay? Yeah. So if I want to get the pulse transfer function, I'm going to have to basically, when you put them together, you put things in a pair, right? Now this is y of t, and of course this is y of s. So you can't put these two together. If you put these two together, you get basically the original Laplace transfer function, but that's not the pulse transfer we're looking at here. So what we need is, we need another, some kind of, you can imagine yourself, there's another sampler here, impulse sampler. And that impulse sampler produce y star of t and corresponding y star of s. Okay? Yeah. So then altogether, your your impulse, okay, your impulse transfer function is actually a relationship between the output here and the input at here. Okay? So basically between the two starred one there. Okay? So but you know, the other thing is, let's relate to the actual if I relate to the actual system, let's just say, maybe give you an example here. This impulse sampler in actual system, well, what could that be? It could actually just be a simple what? Analog to digital converter, right? Yeah. So let's say you don't have a controller at all. You know, all you do is let's just play with it. I'm gonna sample the input voltage. Okay, just sample it without processing it, without programming at all. In basically, and then I wanted to send it out back into a continuous system. Okay, you see what I'm saying? So technically speaking, you got to have a certain kind of controller here, right? Or you got to have a difference equation because this is discrete now. But if you just say, I don't want to insert anything, I just want to send it right away back into the certain system. But you can't send it right back to it, right? Let's say this is a plant G of S. Okay, you can't send it right back to it because this is discrete one. So what do we insert here? We insert a digital to analog, right? Or in other words, basically we're inserting. You can insert what? A block like the order hold, essentially. So this digital to analog, it's too simple, but the functionality, if you want to basically, before you send it back right to this continuous system, you're gonna have to hold it, right? Yeah, to make it continuous now. Dan, you have a question? Yeah. Yeah, exactly. So then you get certain output. Does that make sense, right? This is basically the most ridiculous kind of a control for the system, but it's okay, right? Yeah. But if you look at all together here, basically you see I do have a math model for the order hold, isn't it, right? Yeah. So I can basically combine these two. I can call these two as H of S. Okay. Does that make sense? Yeah. So this is essentially where this block could be from, right? Yeah. Now regarding this sampler, impulse sampler here, I mean, if you imagine you send the signal back into the continuous system, and the system has a certain output. So technically speaking, you don't really need to know what the discrete one anymore, right? All you care is what's the current output. It's a continuous system, that's fine, right? So this sampler here, it's more or less, it's a very fictitious one. It's just for your math derivation here. So temporarily, you imagine you're inserting an impulse sampler at here. You see what I'm saying? Well, the purpose is trying to generate this function. Okay? Yeah. So it doesn't have to practically exist, but this one has to, right? This one has to. So this one doesn't have to practically exist. Okay? Yeah. Okay, so now let's look at this guy here. So let's look at what will be the pulse transfer function, right? Yeah. Okay, so a couple of facts. Okay, a couple of facts. Basically, before we do, without giving the further proof, you can look at the textbook for proving. So x star of s, if you remember that, okay, this is a star Laplace transform. Okay, Laplace transform. So x star of s, okay, between the x star of s and the regional x of s, I think we derived this one. Actually, I didn't derive this one, but you can take a look at the textbook. Okay, the relationship between x star of s and an x of s is this. Okay, this is the relationship between the x star of s and x of s. Okay, so basically, if from a continuous point of view, this is x of t, and x star of t is a sequence of right, impulses, right? Yeah. So I think you learned actually in particular for electrical students, you learned the Fourier Transform. You learned the concept of frequency spectrum. So if I replace this S with J omega, okay, replace both sides with J omega, then if we plot this frequency spectrum, okay, basically the magnitude of that, right? So for this continuous, let's put this one here for the first one, not star. From x of t to here, okay, from x of t to here, let's just say that you have something like this, right? Yeah, and this is the omega axis, right? Yeah. So for any system, you will always have certain bandwidth. So the bandwidth here, let's see, is omega 1. Is that good? Yeah. Then the difference between these two basically is an impulse sampler, right? Okay. Then if you take the same thing, okay, basically looking at the frequency spectrum for now, this is going to be what? X star of J omega now, right? X star of J omega. Okay? Yeah. So the difference now is so this is the bump like here. The magnitude might be different. Okay? Yeah. And then you have another bump. Okay? So it's a bit of small now, basically keeps going, right? Like that. Okay? And the second bump center is at the omega s. Omega s is, what's omega s? It's a sampling frequency. Okay? And in the center here, this is basically what? Omega s over 2. Okay? That makes sense? Yeah? So, now actually my purpose is to remind you a very important theory, which we don't really need it, but we generally should bear in mind though, right? So tell me, what's the theory? Nyquist theory, right? Yeah. So, imagine yourself, right? If your sampling frequency is low, then what happens to these two bumps? They will overlap, right? They will overlap. So when they overlap, this is the phenomena we call that. What do we call that again? Aliasing, right? Aliasing. Okay? Yeah. So that's the difference between the x of s and x star of s. All right? Yeah. From here to here? Yeah. Yeah. So basically, the sample, the different names, something called a Shannon theory, Nyquist theory, or sampling theorem, right? But basically what happens is, if you want to, the idea is, I don't want to write anymore, just repeat it. If you want to reconstruct your original signal, okay, based on the first sampled ones there, okay, then your sampling frequency, right, has to be at least, okay, half of, at least twice of the bandwidth of your system, okay. Yeah. So because you see what happens is, so what happens is from here is, let's say here is from here to here, right? And then I want it to from here back to here. So technically speaking, if I wanted to go from here back over here, so what do I need? I need what? A filter, which is actually you need so-called, right, a low-pass filter, right? Yeah. Now, if these two bumps overlapping each other, then what's coming out of the low-pass filter will not be exactly the same as the original bump, basically. Okay? Yeah. So that's the idea. So, and the other thing is, okay, we can use the opportunity here is basically, mathematically, you can also do, so from x star of t, okay, from x star of t to x star of j omega. Okay, so you know you have the x star of t. How do I, and that's your signal. how do I get this x star of j omega? You can use a fast Fourier transform, to get to this x star of j omega, right? And as I said, you can use a low-pass filter to get back to this x of j omega, right? Then from x j omega, if I want to get back to x of t, and you can try what? The inverse fast Fourier transform. Okay? Yeah. So those are basically the connection here. Okay? The connections. But one thing is, this is basically something I don't need to prove. But you see, the difference basically is what I explained here. Here's a pump, but after this here, this is basically repeated, right? This periodic things here, right? Okay. Okay. So let's come back over here. Come back to this diagram here. Okay. Come back to the diagram. So purely based on the diagram, look at this one here. What is the value of y of s? Y of a small s equal to what? The signal. Equal to this block times the input, right? Times input. Okay? Yeah. So h of s times x star of s. Okay? Yeah. So let me come back here. So y of s equal to h of s times what is it, right? X star of s. Okay? Yeah. So now here's basically the next operation. I'm gonna take basically called start. Okay, start operation. This is the next. I'll take the start operation. So it's a sort of like a transformation. Okay. So what I mean is, I'm gonna basically take the start operation on this side here, and take the start operation on this side here. Okay. Yeah. Because the objective. Remember, what's the objective? The objective is actually trying to bring everything into the same page. I don't want to deal with the star or on star or the no star one, right? I want to put everything into the star basically. Okay? Yeah. So without a proof here, I can tell you. Okay. Basically, you can prove this. The proof is part of it in the lecture notes and part in your textbook. So when you have this kind of case here, this is basically h star of s and x star of s. Okay, it's this guy here. Is that okay? Yeah. Now, just be careful though, huh? The operation works only when you have these two blocks. Here's h of s, x star of. If you have this kind of case, let's say for example, if you have a case star g1 of s and g2 of s, x star of s, okay, and then you take the star, okay, then you take the star. It doesn't give you g1 star times g2 star times x star, okay. So what do you have to do? You have to put these two together first, right? So let's say this is g1 g2 s. Okay, and then you get g1 g2 star x star. Is that good? Okay, that's what you need to be careful for, right? Yeah. So coming out of here, now you see I have everything in terms of star now, right? Everything in terms of star. Then we want the pulse transfer function. That's basically a transfer function in terms of z. So what do? We get this h star of s equal to y star of s over x star of s. Okay? So from here you can obtain this h of z, right, by replace the small s with the 1 over t ln z. Okay? Then you get y of z over x of z, similarly like that. Okay? So this is the pulse transfer function, right? For that simple module. So it seems actually a bit of redundant, but when we put everything, lots of things into a more complicated loop, okay, we need this simple concept. Okay, is that good? Yeah. So basically, the idea, one of the key points here is, okay, one of this, how you do this start operation. Okay. All right, so now let's look at one example here. Okay, yeah, by plugging some kind of which actually I draw this one already. So basically, it's the same diagram I draw. Here I have a zero order hold. Here is a plant. Okay, here's a plant. What is the pulse transfer function for this simple open loop system? Okay, for this simple open loop system. I mean, basically, this is the h of s that we just written there, right? Just written there. Okay. But this is a special one because there's a zero order hold here, and inevitably you will have a zero order hold, and we'll see the results. Okay, of this example. You don't need to rewrite or derive every time anymore. You will have to remember the results from this example. All right. Yeah. Okay. So what is h of s first of all? Which is what? This times this. Right? This times this. And we can do a little bit of simplification in here, just to rewrite this. Okay, is that good? Yeah. So we want the pulse transfer function. So based on the previous example here, okay, previous example, you look at this one here. Basically, that block that I just draw is the same kind of block like this, right? The same block like this. So when you have a block like this, what's the pulse transfer function we just derived? It's this is h of s, right? This is h of s. So the pulse transfer function is h of z, okay? And it's of course corresponding to h star of s, right? Corresponding to h star of s. So basically, for this particular one here, the pulse transfer function is h of z, right? H of z. Okay. And h of z come from h star of s by replacing the s 1 over t ln z. Okay. Yeah. However, we don't have h star of s, right? We don't have h star of s. We only have h of s. Okay. So basically, the question here is, okay, how do we get this h of z, okay, right, to from h of s? Is that good? Yeah. So there are two ways of doing this. Okay. So the first one is, here's h of s. First, we obtain h star of s. Okay. This is the first approach. Okay. Now this approach, I'll tell you a formula, okay, which you will practice just a little bit in one of the assignments here. Okay, so this is basically a formula also from the textbook on page 84 to 87. Okay. So here's the formula. So h star of s, okay, equal to this. Residual of h of lambda times 1 over at whole lambda equal to lambda 1 of h of lambda. Okay, so that's the formula. Okay, it seems pretty simple, but I'll explain what this means here. Okay, yeah. So h star of s equal to the residues of this guy at the poles lambda equal to lambda 1 of this trunk. All right, yeah. So basically, what you do first is you replace this. You see, this is talking about h of lambda, right? So the first step is basically you change this to h of lambda or any other symbols you want. Okay, any other symbols. Then you multiply this h of lambda with this guy. Okay, with this guy. Okay, so let me give you an example here. So let's just say use a simple one here. Okay, suppose that this is my h of s. Okay, so first step, we change that to lambda. Okay, we change to lambda. Then we times this with 1 over e to the power of negative sampling time capital T, then s minus lambda. Okay, yeah. So that's basically this chunk right here. Okay. So now talking about the residues of this guy, right? Talking about the residues of this guy. So the residues of this guy. So there. First of all, how many poles here? We have 2 poles, right? So poles lambda 1 equal to -1 and lambda 2 equal to -2. So in this case here, basically, how many residues? We will have 2 residues. Okay, yeah. So the first residue, so the residue number 1, let's call that K1. Okay, residue number 1, K1. So according to the formula, right? According to the formula, what you do is, okay, residue of this guy at this pole here. And that's basically the same way as you doing the partial fraction. Remember the a and the b. So how did I get an a again? I multiply the denominator, right? And then times the original one, and replace the pole, right, with the pole's value. So in this case here, what you do is, here you're talking about the residue corresponding to this one here. So what you do is you should do lambda plus 1 times this whole chunk. Okay, times this whole chunk. So apparently when you this guy times, let's see, I'll just write here, times h of lambda 1 over, okay, like this, right? Like this. So you cancel this lambda plus 1, right? And then you let lambda equal to -1. Okay? So you can imagine when you plug in the lambda equal to -1 here, so what do we end up with now? Everything else except the variable s, right? Except s. Okay? So you end up with the s function, which is what we want. We want to end up with the s function. Okay? Yeah. So you can try that. Okay? You can try basically plug it in here. You'll get the so-called h star of s, right? So the last step, right, is to do what? Replace the s with 1 over t ln z. Okay? So you might think, okay, so what does that lead to me? Actually, you know what? You see here, this is e to the power negative t s minus lambda here, right? Just for example, this is e to the power negative t. If I plug lambda equal to -1 here, this is what? Plus 1, right? Plus 1. Okay? So, what do we get from here? This is e to the power of negative ts times e to the power of negative t, right? So negative t, sampling time t, you will know that. So, oops. So you will know that. So this is going to be constant, right? It's going to be constant. So then, when you replace the s equal to 1 over t ln z into here, what do you end up with? S equal to 1 over t ln z. Well, look at that. So this t, they cancel, right? Yeah. So this is e to the power negative ln z. Now what is the e to the power of negative ln z? Huh? 1 over z, yeah. Yeah? So see, negative ln z equal to ln z to the power of -1. Okay? Yeah. So basically you end up with just a pure z function now. If you do these steps. Is that good? Okay, that's the first approach. Okay, yeah. So getting from h of s to h star of s, and then from h star of s to h of z. Second approach is to use a table again, to use the Ztransform table. Okay, Ztransform table. So remember, when I learned the Z-transform, when I teach the Z-transform, I said, okay, so where does the Z-transform from? Okay, so it's from a sequence of a number, right? It's from a sequence number. And I can also write it's from where? It's from the time function, right? And I can also write it's from where? It's from its corresponding Laplace transform. Okay? Right? So the underlying meaning, basically, when we write this one here, when we write particularly this guy, okay? It's like a backward here. When you write the Z of this guy, you actually means this. You actually means, okay, I'm gonna basically transform this back to h of t, and then I do an impulse sampling of this, and then I get this. Seriously, right? Yeah, that's what the underlying words. However, okay, what simplified the situation is, you see here, right? In the table, if you look in your table, you have the simplest form of h of s x of s, right? You have this one here. If I say, okay, what is the 1 over s z transform? It's that, right? What is this guy? It's that, right? Something like that. So basically what this means is, if I can simplify this guy into the simplest format, then I can use a table to find h of z, right? Yeah. So now let's try this one, this approach for this example right here. Okay. So what h of s we're dealing with? We're dealing with we're dealing with this h of s here. Okay. All right. So this one doesn't seem to have what you need from the table. Okay. But I guess we can do a little bit of simplification first. So I'll multiply this temporarily. I'll let g of s over s. Okay. Temporarily, I'll let this guy to be one function g1 of s. Okay. So 1 times g1 of s minus e to the power of negative t g1 of s. Okay, like this. So the two terms here, you basically means you have 2 z here. Look it, right? Yeah, 2z form here. The first one, we don't know what this function. We don't have exactly the expression given for this g of s, right? But if we do, we can basically simplify that, to look at the table here. But ultimately, let's just see, this give me g1 of z, right? It'll give me a g1 of z here. Okay. Yeah. And what is the g1 of z? So basically, g1 of z is what? Is a g over, it's the z operating on this guy, right? You get that this g1 of z, right? Okay. Yeah. Okay, so the operation is this one here. E to the power of negative ts times g1 of s at here. Okay, g1 of s. Now, if you recall that, in discrete system, when you have a delay, when you have a delay, the corresponding Z transform always has a Z to the power of a negative certain quantity, right? If it's Z to the power of negative 1, so chances will tell you the original system has a delay of 1 step, right? So when you have a continuous system, there's a time-delayed continuous system. How does that show up in the Laplace? Here. Okay? So when you see exponential function like this, that basically tells you the original time function, there is a time delay. How much delay? T. Okay? So basically what you're dealing with here is, let's just say this g1 of s corresponding to a g1 of t time function, right? g1 of t time function. So if you transform it back to a time function, there will be a time delay, okay, capital T. Okay, so then remember what you do from here now. You basically, you will sample this, right? You will sample this here, right? You sample this, okay? Now, from here to here, then apparently you see there is what? A one-step delay, right? One-step delay. And what is the Z-transform for this guy? Using your table on the other side of the table, whenever you have one-step delay, the corresponding Z-transform is Z to the power -1 times what? G1 of Z. Okay? Does that make sense? Right? See, this is a G. This one here. This one here is Z G1 of T. Okay? Yeah. Give you this. And here is different differences. This is a one-step delay. So you just simply plug in this right here. If it is 2t, -2, like that. Okay? Okay? So now this is your h of z, right? This is your h of z. So what is h of z equal to now? It's 1 minus this g1 of z, which is, what is g1 of z again? It's what? G of s over s, right? It's this. So what I need you to remember, basically, is this now. So first of all, what we're dealing with is there is a zero order hold at here, okay? And there is a impulse sampler in front of it, and there is a transfer function somehow over here, okay? Then when you try to transform it into the z, or trying to get the pulse transfer function, then first of all, basically you're dealing with multiplying them together. Then the z transfer function or pulse transfer function, okay, for this whole expression in here, end up with 1 minus z to the power -1 z g of s over s. Okay, so you don't need to rewrite everything anymore, right? Yeah, all you need to remember is just this is the final formula, basically. Is that good? So let me give you a more concrete example now, just to plug in this case here. Okay, let's say I'll give you one simple example here. Let's say this is my system G of s. This is G of s, which is 1 over s plus 1. Okay, it's a first order system. It's a very typical. You see that in velocity control of a motor, okay, first order system, okay. Then, according to my final result, right? According to my final result, the pulse transfer function, okay, for that particular one is, which is what? Then it will be 1 minus this and z. So 1 over s plus 1, then times this s. Okay. Is that okay? Yeah. So the question is, what will be the Z transform for this one? I think you have one in the table. Yeah, you have one in the table. Right here, right? Right here. So the A value at here is 1, right? A value is 1. Okay. If your A is not 1, let's see if this is a plus 2 at here, you actually have to time a 2 first, and then divide it by 2, right? To match that table. Okay. But either way, what will be the Z transform of this big chunk? What do we get? It's right here, right? Right here. So, oh yeah. Okay. So you can always simplify though, huh? This 1 minus z to the power of -1, which is this. Okay? And times this. So guys, look at that you can cancel this z, you can cancel this z minus 1, so you actually end up with so that's the final result if you plug in your g of s as 1 over s plus 1. Okay, cool? Yeah. So for this one particular system, you only have one pole, and that pole location is at here, and the pole is always greater than 0, right? Yeah. And that pole is actually always less than 1. Does that make sense? This pole is always less than 1. This is exponential decay, right? So if you plug the t in as a 0, what do you get? You get 1, right? And t cannot be less than 0. T is always greater than 0. So as t is growing, this is going to be always decaying, right? So that's why it's always less than 1. So this one is a little bit funny though. See, t is closer to 0, meaning sampling time is pretty fast, right? So when sampling time is pretty fast, you're supposed to get a good approximation of the original system. Okay? Yeah. But when t is a bigger value, you get a pole close to what? 0, right? And later we'll learn that when your pole is closer to 0, the response is actually, that's for the z domain, okay, not for the s domain. The response is actually faster. Okay, and so basically the sequence number, you'll see that it decreases faster, right? Yeah. So higher sampling time in this case have a higher decay in the sequence number. Okay. Okay. So any questions? It's all good. So, right, that's a simple example of open loop, right? This is open loop pulse transfer function. Now, in MATLAB, there is a very useful command that you will use. Basically, let's say for example, right? If I'm dealing with s plus 2, okay, and I'm trying to convert this, okay, trying to obtain the Z transform, of this one here, with the sampling time of t equal to 1 second. Alright? So, of course, you can use a table. It's very simple. But in the MATLAB, you can do is let's say, set the sampling time to 1 first, create, okay, a transfer function first for this one. So let's say you create the transfer function. Okay. So when you create this transfer function here, you can create 1. The numerator here, the coefficient is only 1. The denominator here, the coefficient is 1, 2, right? It's 1, 2. Okay, that's how you can create this. Okay, yeah. And the next step, okay, I should call this C, probably continuous system and discrete system. Okay, it's to use this command called C to D, basically continuous to discrete. Okay, and the C to D takes the transfer function that you just created. Okay, it's a numerator denominator. Now plugging the sampling time, and very importantly, okay, having a command like this, IMP. IMP meaning impulse. Okay, impulse here. Is that good? Okay, so what if I have a zero order hole in front of this guy here, like the example that we just did. Okay, like the example just did. Then you say, okay, what would be the pulse transfer function, right? Like in our example there. And what you do is, in this case, everything the same thing. C to D, SYSC, TS, same thing. The option in here, ZOH. Okay. So when you use option ZOH here, the MATLAB will automatically insert the zero order, hold it here, and then calculate the results, and you will get this. Okay, so try it for that particular example, right? See if you can get the results like this here. Is that good? Yeah. So try it. Okay. You will use this several places of assignments. Okay. Yeah. Okay. So let's keep going a little bit here. Okay. Yeah, that's the material. Any questions? All good? All right. So let's keep going on this open loop pulse transfer function, right? So now let's look at a little bit more complicated open loop. Okay. Yeah. So okay. So this time I'm gonna deal with, let's see. I will deal with a little bit more complicated open loop. We have input x of t, and we have output y of t, and this is what we call y star of t, right? That's what we call y star of t. Okay, so what's the difference now is basically you have one extra sampler and then one block here, right? One block here. Okay. Yeah. So what would be the pulse transfer function for this open loop system? Okay. The one difference often makes the discrete time control system is the system is always a mix of analog and the digitals, right? Always a mix. Okay. So ultimately, in this particular case, what you need to compare is you need to find what is the relationship between y star of s and x star of s, right? If we can figure this out, and that's my h star of s, and we can just basically replace the s back to z, right? Find the pulse transfer function. Okay? Yeah. So what you need to do is basically go over this diagram, okay, to find the relationship. This is x of t after sampler x star. Then after this g of s, at here, what's the signal? Is that a star signal? Is that a regular time signal? At here. Yeah. So let's call that, give a symbol here, u of t. Then after this another sampler, this is u star of t, right? Yeah. Okay. And after this y of t, looks like this. Okay, is that good? Yeah. Okay, so going backwards, or it doesn't matter. What you can do now is you can write this as x star of s, u of s, u star of s, y of s, something like that. Okay. So between each block, right? What is u of s? U of s equal this block time this block, right? And what will be the y star? What will be the y of s? It's h of s times this guy here, right? This guy, which is u star of s, right? Okay. Yeah. Okay. So for this particular one here, let's take start operation. Start operation. Okay, start operation. This one here, take the start operation. Okay. Okay. So for this one, the start operation give me x star, g star, right? And this one here give me h star and u star. So apparently, see, where's the u star of s? Here, right? It's this. And I can plug it into here, right? So ultimately, what do we get for y star of s? We get h star of s times x star of s, and then well, let's maybe write g first. Okay? Yeah. So everything is start. You know, that's perfect, right? So the ratio between y star and x star is, it's this, right? Well, I guess I shouldn't call it h of s because there's already h of s here, right? Yeah. I don't know. Let's just call it the ratio y star or x star. Okay. So this is basically your transfer function. Pulse transfer function is y of z over x of z equal h of z g of z. Okay, h of g of z. Okay, is that clear? So take a second look at this diagram here. Okay, why is it so nice in this case? It's just simply this h of z times this g of z. Why it's so nice here? It's because you look at this one here. This block and then this block, right? The commonality, basically they are separated by what? By this impulse samplers here, right? Yeah. So essentially, whenever you have a certain h of z, t of z, s of z, y of z, whatever, right? You actually should imagine there's impulse sampler, right, within that block there. Okay. Yeah. So if this is the case, you know, whenever they're separated by a impulse sampler, then there are two z function. You can multiply them together essentially. Okay. Yeah. So if you imagine this, right? If this is a g1 of s followed by a g2 of s block, okay, g1 of s followed by a g2 of s block, then what do you have to do? You have to multiply the g1 and g2, right? Put them into one thing first, right? Put them in one thing. Okay. Okay, so almost running out of time. Yeah, you have a little bit disadvantage because I have a class right after 9:30. And my computer always need a bit of time to set it up. It's just so let's not let's go over this maybe. Okay. Quickly. Now this is nothing new actually, okay? It's more of a practice. Alright, so I'll give you a slightly different block, okay, 0 order hold, a plant, and then a digital controller here, okay, a digital controller. Okay. So the digital controller, this is basically, let's see, what's coming out of here. Let's see, this is M of K, okay, discrete one here. Okay, so then this is the digital controller typically can be expressed or can be programmed using difference equation, right? Difference equation. So in this particular case, my difference equation is this. So this is the d of z. Okay, that difference equation here. And this is what you're going to program, into the microcontroller, right? And GP of s, as before, it's 1 over s plus 1. Then what will be the pulse transfer function, okay, for this system here? So let's see what's coming out of here is a c of t. Okay, c of t here. What will be the pulse transfer function of this system? So this is a typical mixture of analog and the digital system, right? So this is analog here, and this is digital, right? Okay. And this sampler here, as you recall that, basically that's your AD, right? And this zero order hold could be just a DA, okay? Okay, so first step, you have to obtain what D of Z is, right? What D of Z. So D of Z equal to what? The output over the input, okay? And you have the difference equation. You have a difference equation. So when you have the difference equation, you can take the Z transform of both sides of this. You see what I'm saying? Okay, take the Z transform both sides. And the Z transform this side is M of Z. The Z transform here, E, this is what you get. You get 2 E of Z minus what? Z to the power of -1, right? And the E of Z. Okay? So you'll get a ratio between M of Z and E of Z, and in this case you get 2Z minus 1 over Z. Okay? That's D of Z. So now you can see, can you imagine what do you do from here now? If I call this whole chunk as G of S, okay? I call this whole chunk G of S here. What do I need to do first? I need to convert this G of S, right, into this the same symbol as the Z first. Okay? So basically you need to find what is the Z of this. Okay? What is Z of this? Is that good? Yeah. I think we did already, right? In the previous example, zero order hold and a Y of this. Making use this formula now. So what's the Z of this? Y minus Z -1 times what? In this case, this is 1 over S plus 1. This is basically 1 over S plus 1, right? Yeah. So the results, you can use the results from previous example. Okay? Yeah. So once you find this out, let's call this as G of Z. Okay? Let's call this as G of Z. So once you find this out, then this G of Z times that D of Z is the pulse transfer function. Okay? Yeah. So pulse transfer function is C of Z over E of Z. So output over input equal this D of Z times this G of Z. Okay, that's the result. So you can try to practice this yourself at here, right? Yeah. Okay, so any questions? Yeah? Good. So I'm giving out the first assignment. Okay, you have 2 weeks to finish. Okay, this is basically based on this week's lecture. All right, and an open loop system. Okay. Oh, good? All right, see you next week.